Good evening, everybody. So, good evening, Lakshmi, Tejasvi, uh, Kanapurugiri. Can you hear me? Yes, please tell me, can you hear me? Can you hear me, guys? Hello, Shashikala. Good evening. Okay, then. So, today we are going to talk about the common forces in mechanics. In last few lectures, we studied Newton's laws of motion, and the laws of motion are all about what? The forces. Okay, so let's talk about the common forces that we encounter in problems in physics or mechanics. So, the forces can be classified into two categories: contact forces and non-contact forces. So, what are contact forces and non-contact forces? The contact forces are the forces for which you need to have contact between two bodies. Okay, so you need to have a contact between a body which is exerting a force and a body which is experiencing that force. Okay, and there are some forces which need not have contact between two bodies in order to exert the force. So those forces are implemented due to the fields. Okay, for an example, what are non-contact forces? Okay, anybody can tell me what are non-contact forces, or which forces you don't need to have contact between two bodies? Please comment. Magnetic force, right? Anything else? Magnetic and gravitational force, right? Okay, so we daily experience gravitational force. So what are non-contact forces? Some examples are the gravitational force, then the electrostatic force, and magnetic force. Okay, these are some examples of non-contact forces. So if there is no contact between two bodies, then how do one body or one particle exerts force on the other particle? So if we consider an example of the gravitational force, then if we have any mass, okay, any particle having mass, then it creates its gravitational field in surrounding region. Okay, so it creates its effect in the surrounding region, and whenever the other body comes in that surrounding region, then due to that effect of first body, it experiences a force. Okay, the effect is called as field. So there are gravitational fields present everywhere, then the electrostatic and magnetic fields. So what do we say? We call them electromagnetic fields. Okay, so what are examples of contact forces? Any examples? We have seen some of them. Muscular force, right? It is an example of contact force. Okay, anything else? Okay, so let's see some examples. One example is normal reaction. Okay, then the spring force, then tension in a string, okay, then drag force due to a medium, okay. All of these are examples of contact forces. So for all of these forces, we need to have contact between two bodies. Okay, so now let's talk about these forces one by one in brief. So let's talk about the gravitational force first. So what is gravitational force? Now according to the Newton's universal law of gravity, every particle in the universe attracts every other particle in the universe, and the force of attraction is directly proportional to the product of masses of the two particles, and it is inversely proportional to the square of distance between them. Okay, so according to Newton, every particle or every body in the universe, it attracts every other body in the universe, and the force of attraction between them is known as the gravitational force. Okay, so this gravitational force is directly proportional to the product of masses of two bodies. So it is directly proportional to, let's say, mass of first body is m1, mass of second body is m2. So the gravitational force is proportional to m1 m2, and it is inversely proportional to the square of distance between the two bodies. So suppose this is first body, this is second body, their masses are m1 and m2, and distance between them is r. So this force is inversely proportional to the square of this distance. Okay, so if we combine these two, we can write the force is proportional to m1 times m2 over r squared, and if we remove this proportionality sign, an equality sign will come in, sorry, a constant will come in. So if we remove this proportionality sign and put an equality sign, a constant will come in. The constant is known as the universal gravitational constant, and it is denoted by this letter capital G. Okay, so F is equal to G times m1 m2 over r squared. Okay, so now this constant is known as the universal gravitational constant. It means that why this constant is known as the universal gravitational constant? It's because this constant is constant everywhere in the universe. Okay, that's why it is known as universal gravitational constant. All right, so the force is directly proportional to the product of two masses and inversely proportional to the square of distance between them. So this is Newton's law of gravitation. Okay, so now let's suppose this is Earth and this is any body. Okay, let's suppose this is a stone. So how do we write gravitational force acting on this stone due to Earth? So you might have seen we write the force acting on this stone due to Earth equals to mass of this stone multiplied by acceleration due to gravity. Okay, m multiplied by g, and we know that this g is equal to what? 9.8 meters per second squared. Okay, so here we have seen that the gravitational force is directly proportional to the product of masses and it is inversely proportional to the square of distance between two bodies. But in many problems we encountered till now, we have considered gravitational force equals to what? M times g. Okay, we consider this acceleration due to gravity g equals to 9.8 meters per second squared, and roughly we take it as 10. Okay, so if force is inversely proportional to the square of distance, then why don't we consider that force is varying? Okay, why do we consider that the force is constant? It is m multiplied by g. Anybody? So have you got my question or shall I repeat it? Yes. It's because of mass, g is constant. No, no. See, okay, let me add a page over here. Okay, so what I am saying is the gravitational force is equal to g into m1 m2 over r squared. So now suppose capital M is mass of Earth, okay, small m is the mass of this stone, okay. So this is Earth, this is that stone. So the gravitational force between this mass m and this mass capital M of Earth is equal to what? G times capital M into small m over r squared. Okay. So now we can write this as the force acting on this mass is equal to what? This m multiplied by its acceleration, and acceleration is due to this gravitational force, so I can write this as m times g. Okay. So here, if you cancel out this m and m, what do you get? You get g is equal to g into m over r squared. Okay. So r is the distance between center of the stone to the center of Earth. Okay, this is r. So this g is inversely proportional to r square, but no matter, but in practice what we do is, in many problems, let's suppose this mass is at height of, let's say, 100 meters. Okay, so suppose this height is 100 meters, then this g will be smaller. Okay, because compared to the object on the Earth's surface, this mass is a little bit away compared to this object on Earth's surface. This mass is a little bit away from Earth's center. Okay, so then this acceleration due to gravity is inversely proportional to r square. But why do we consider it to be constant? Okay, in many problems, so let's suppose we consider in practice that on Earth's surface and at height of, let's say, 100 meters, the acceleration due to gravity is same. So how can we do that? Okay, please try to answer. Okay, Mitul is saying, hi sir, I am Preet from 9th standard, and okay, for 9th standard. Okay, Mitul, if I get some time, I will teach. Okay. So right now, actually, I'm taking only 11th standard physics, and that too 3 times a week. Yes, anybody? Okay, let me answer this. So, in problems involving heights which are very small compared to the radius of Earth, so if h is very small compared to Earth's radius, the distance is not changing that much compared to this distance. Okay, so whether the body is on Earth's surface or the body is at height of 100 meters, there is not much change in distance compared to the radius of Earth. The radius of Earth is so big, okay, that there won't be much change in the acceleration due to gravity. All right, so that's why we consider it to be a constant. Okay, in problems involving small heights, we consider that acceleration due to gravity is fairly constant. Okay, so is it clear? Yes. For others, is it clear? Okay. So what I am saying is the acceleration due to gravity, it's inversely proportional to the square of distance between two bodies. Okay. How do we know that? The gravitational force is gmm over r squared, and the gravitational I'm sorry, the gravitational force acting on this mass small m due to the earth will be equal to what? Mass multiplied by acceleration. Okay, so it is m times g, the acceleration due to gravity. Okay, so we can cancel out this m and m. So g depends on the universal gravitational constant. It is a constant. Mass of earth, capital M, and this r. So what is r? R is distance between two bodies. Okay, but now in practice what we do is, for small heights, for 100 meters or so, we consider g to be equal to what? 9.8 meters per second squared. So how this thing is justified? Actually g should change as distance between two bodies changes. Okay, on earth's surface the distance between that stone and center of earth is small compared to when we take that object, that stone, at the height of, let's say, 100 meters. Okay, so acceleration due to gravity, it's inversely proportional to r squared. So the acceleration due to gravity at that height will be smaller compared to what? The acceleration due to gravity on earth's surface, because we are taking that object away. All right, but now we consider it to be constant, and it is justified because the earth's radius is very large compared to this height. Okay, or let's say height of 100 meters, 200 meters. Okay, so there is not that much change in distance. So is this clear now? Yes. Yes. Okay, good. So now let's talk about the electrostatic force. So what is electrostatic force? It is force between two charges. Okay, so if we consider two charged particles, so this is one particle and this is another particle. So suppose q1 is charged on the first particle, q2 is charged on second particle. Then we have learned in this in lower standards that like charges repel each other and unlike charges attract each other. Okay, so the force of attraction or repulsion between these charges is given by a law which is known as the Coulomb's law. Okay, and the Coulomb's law reads, the force of attraction or repulsion between two charged particles is directly proportional to the product of their charges, and it is inversely proportional to the square of distance between them. So you spotted some similarity with the gravitational force. Okay, this law is very similar to that of the Newton's law of gravity. So the force can be written as, the electrostatic force can be written as what? Okay, let's write it like this. It's directly proportional to the product of two charges, and it is inversely proportional to r squared, the square of distance between them. Okay, and the proportionality constant here is suppose k. So we get F equals to k multiplied by q1 q2 over r squared. Okay, and this k is 9 multiplied by 10 raised to 9, and the unit is Newton meter squared divided by Coulomb squared. So Coulomb is unit of charge. Alright, so as charges come close to each other, what happens? The force of attraction or repulsion between them increases. As they go away, the force between them decreases. Clear? Should we apply direction symbol? Okay, charges are scalar quantities, but the force is vector. Alright, so now the direction of this force will be along this line. The attraction or repulsion, it will take place along this line, right? So now if we put the values of q1 and q2, if both of them are positive or both of them are negative, then the force will be positive, and positive means repulsive force. Okay, so positive means that q1 is pushing q2 towards right hand side, and q2 is pushing q1 towards left hand side. And if one of them has opposite sign, that means if one of them is positive and other one is negative, then this product will have negative sign. So negative means an attractive force. Okay, so negative means q1 will pull q2 towards it, and q2 will pull q1 towards it. So the direction of this force is taken care by the the direction of this force is taken care by the positive or negative sign. Does this answer your question? Yes. I'm sorry. Okay, does this answer your question? Is it clear to everybody? Good. So for others, is it clear? Okay, so now let's talk about the spring force. Okay, next let us talk about the spring force. So what is spring force? So from day to day, sorry. So if you have a spring and you compress it, then what happens? The spring tries to push your hands outwards, and if you stretch it, if you elongate it, then what happens? It pulls your hands inwards. Okay, that means there is a restoring force generated in the spring, and that force is known as the spring force. Okay, so here we have considered a block which is connected to the spring, and it is resting on this horizontal surface, and the other end of the spring is connected to this rigid support. Okay, so in equilibrium, so equilibrium means when sum of all forces acting on a body is zero, so spring will be in its natural condition. It will not be compressed or it will not be elongated. Okay, so under equilibrium, the spring will be in its natural state. Okay, so now when we pull this block, let's say towards right, what happens? The spring gets stretched. Okay, so the force exerted, the external force exerted is in this direction, and the spring, it wants to come back to its initial condition. So there is a restoring force generated in the spring which pulls it back. Okay, and that restoring force is directly proportional to the distance with which the spring gets elongated. All right, so similarly, when we push this block in this direction, the external force is towards left, so spring gets compressed and it wants to come back to its initial condition, so it pushes the block in outward direction, okay, towards right. All right, so the restoring force or the spring force is always directed opposite to that of the external force. Okay, yes, Gangadharan, it is present in NCERT. Is that force named as tension? No, tension is for strings, for ropes. Okay, so now the restoring force generated in spring is called as spring force, F suffix s, and it is directly proportional to the displacement of the spring. Okay, so it is directly proportional to x, but it is directed opposite to that of x, so to take care of the sign we put negative sign. Okay, so the restoring force in spring, the spring force, is directly proportional to what? Minus of x. So now if we remove this proportionality sign and put an equality sign, again a constant will come, and that constant is known as spring constant. Okay, so constant is k, so Fs equals to minus of k into x. So this k is known as the spring constant. And it depends on the spring. Okay, it depends on the material of spring, thickness of spring, etc. So is this clear? Okay, this video cannot be downloaded. This video is not uploaded yet. Okay, so this is live right now. So once it gets uploaded, after that you can download it. Maybe tomorrow you can download it. Okay, so now we have seen that the spring force is directly proportional to the displacement of the spring. So This law is known as the Hooke's law. Okay, the law which tells us that the spring force is directly proportional to the displacement. It is known as Hooke's law. And it enables us to quantify a force. Okay, till now we have been talking about the force, let's say 10 newtons, 100 newtons, but how do we measure a force? Okay, to measure a force, we need to have some reference. Okay, so spring force provides us with the reference to measure a force. For an example, now let's suppose this is some rigid support and it's connected with a spring. Okay, and we put a mass of, let's say, 1 kg over here. Okay, so due to the gravitational force, what will happen? This mass is pulled downwards and it gets displaced. So it gets displaced up to, let's say, distance x. Okay, so this much is the elongation in the spring. So how much will be the elongation for the mass of 2 kgs? Yes, for 1 kg, the gravitational force is equal to what? The gravitational force which is acting downwards is m into g. So if g is, let's say, 10, the gravitational force is 1 times 10, that is 10 newtons. Okay, so how much will be gravitational force for 2 kg, mass of 2 kg? It will be 20 newtons, right? And if for 10 newtons the elongation in this spring is x, for 20 newtons the elongation will be 2 times of x. Okay, because as we have seen, Hooke's law tells us that the spring force is directly proportional to what? The displacement. Okay, so when this block or when this mass comes to equilibrium, so if when gravitational force acts on this mass, what happens? The spring gets stretched. Okay, and there is restoring force generated in the spring, and the elongation will continue till the time this restoring force which acts upwards balances the gravitational force. Okay, so if for elongation of x, if this block comes to rest, if this mass comes to rest, that means the spring force is equal to what? The gravitational force. Okay, so how much is spring force? It is 10 newtons. So for 10 newtons the elongation is x. So for 20 newtons, how much will be the elongation? It will be 2 times of x. Okay, and now what we can do is we can put the spring like this. We can connect it to this rigid support, and we can take a block like this, and now if we pull this block, okay, with some force which we don't know, okay, let's suppose this spring, let's suppose this block moves from this position to this position. Okay, so now we measure this displacement. So let's suppose this is some delta x, and we let's suppose we already calibrated, we already found that for 10 newtons of force the displacement is x. Then how to find out this f? Okay, so let's suppose this f displaces the spring by delta x. How much will be x? How much will be f? How can we find? Okay, so what we did is we found that for 10 newtons the spring gets elongated by the displacement, okay, x. The spring gets elongated by x. For 20 newtons it will be how much? The elongation in the spring will be 2 times of x. How do we know this? We know this from the Hooke's law. Okay, so my question is, now if we put this spring like this and we put a box, we connect a box to the spring, then we pull this block. Okay, so block moves from this position to this position. So block gets displaced by delta x. How much will be the displacement in spring? It will be also delta x. Okay, the spring will get elongated by delta x. So now can we find out this force? Given all of this information, can we find out this force? Yes, it's simple. See, now if this block is it is pulled to some distance, okay, F will be equal to K times delta X, right? Okay, so using this method we can calculate K, right? We can calibrate the spring, but okay, can I directly say that this force F is equal to delta X over this X times 10 newtons? Okay, because for 10 newtons the displacement is X. So can I say this? If the force is 20 newtons, the displacement will be how much? 2 times of X. Okay, so let's suppose this F is equal to 20 newtons. How much will be delta X? It will be 2 times of X. So delta X divided by X will give us 2. So 2 times of 10 gives us 20 newtons. Okay, so F equals to what? Delta X divided by X multiplied by, let's say, 10. Is it clear? Okay. So what I am saying is the spring force gives us a reference. So if we have a known force, so gravity is the known force, acceleration due to gravity is 9.8, let's say roughly 10 meters per second squared. So we know how much will be the gravitational force acting on, let's say, mass of 1 kg. So when we connect that mass to the spring, we can measure the elongation in the spring and we can calculate the spring constant. Okay, and using that spring now we can measure any force we want. Okay, so now if we exert some force like this, then we just have to measure the elongation in the spring, and now we know Hooke's law. It tells us F is equal to what? Minus of k times x. So using the Hooke's law we can find out this force exerted. Okay, so is this clear? Yes. Okay, so just by comparing the displacements, so for 10 newtons the displacement is x, so for this force the displacement is delta x, so delta x divided by x multiplied by 10 newtons will give me this force. Okay, or what we can do is we can calculate k, and then k times delta x will give us this force. Okay, how do we calculate k? So since Fs is equal to minus of k times x, we can take this x on other side. So k will be equal to what? Minus of Fs divided by x. So under equilibrium, this Fs, the spring force, will be equal to the externally exerted force, which in this case is gravitational force. Okay, so it is 10 divided by x. So this way we can calculate k, we can substitute it over here. So here F will be just equal to what? Minus of k times, okay, not minus, it will be equal to k times of delta x. Okay, the spring force will be equal to minus of k times delta x. So there are two ways, either we calculate k or we compare the displacements, right? So is the thing clear to everybody? Okay, now let's talk about tension in the string. In k times delta x, we should use k equals to 9 into 10 raised to 9. No, 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 no. Oh, see, this k is for the electrostatic force. Okay, I have put same constants. So this k is for the electrostatic force. This k is for spring force. So from the given condition, we have to calculate this k. So if let's say for 10 newtons, if gravitational force is 10 newtons, the spring force will be also equal to 10 newtons, and suppose the displacement is 1. then how much will be K? It will be 10 divided by 1. Okay, 10 newtons per meter. Okay, this K has to be calculated from the given problem. Okay, from experiments. Okay. So now let's look at the tension in the string. So now if we have a string or a rope as shown here, and we hook a mass like this and we hold it, okay, in our hand. So this mass feels the gravitational force and the gravitational force acts downwards. Now in order to keep the mass in equilibrium, we have to pull it, okay, we have to exert an equal and opposite force. Okay, so we exert a force which is equal to the gravitational force, and that force gets exerted on the mass by means of this rope. Okay, so this rope is under a stretching force, okay, and that force is known as tension in the string. All right, so what can be the origin of the tension in the string? So let's talk about origin. So I'm sorry, now at the molecular level, everything is made up of atoms or molecules. Okay, the ropes are made up of molecules, and which in turn are made up of atoms. So in molecules also we have positively charged nuclei. Okay, we have atoms which have positively charged nuclei and negatively charged electron clouds. Okay, so there are negatively charged electrons surrounding the nucleus. So there are many such atoms or molecules in a rope. So let's suppose this is a rope, and then we know that like charges attract each other and unlike charges repel each other. So now let's pick any molecule. Let's pick this molecule over here. So under normal conditions, under the equilibrium, how much will be the force acting on this molecule? Yeah, tension acts along ropes, threads. Okay, so in normal conditions, how much should be the force acting on these molecules? How much will be the net force? Anybody? Okay, let's suppose you have a rope, okay, which is lying idly on some surface. Yeah, so question is, let's suppose you have a rope, okay, you don't stretch it, don't exert any external force, so that rope is made up of molecules as shown over here. So when the rope is lying idly, how much is the net force acting on any molecule in that rope. So for an example, how much will be the force acting on this molecule? Yes, it should be 0, right? So it means that this molecule now, it is surrounded by n number of molecules from all sides. So there is a force acting on this molecule. What do I mean by molecule? The positively charged center, okay, and negatively charged electron clouds. Okay, there are atoms inside molecules, so which have nuclei, okay, and electron clouds. So now the electrons will repel the electrons from surrounding molecules, okay, and they will get attracted by the nuclei, okay, the positively charged centers of other molecules. So let's just say atoms for simplicity. So if we call them atoms, then for wires it will be true, there will be atoms. So there will be repulsion between positively charged centers, the nuclei of one atom, and surrounding atoms. There will be repulsion due to negatively charged electrons of this atom and negatively charged electrons of other atoms. But there will be attraction between this positively charged nucleus of this atom and negatively charged electrons of surrounding atoms. And also there will be attraction between negatively charged electrons of this atom and positively charged electrons in surrounding atoms. Okay, so under equilibrium, what happens? All these forces are balanced, so the distance between these molecules is such that all these forces are balanced. Okay, so we have seen that the electrostatic force, the force between charges, it depends on the distance. If we push the charges closer, the force increases. If we pull them apart, then the force decreases. Okay, so in equilibrium, all of these forces are balanced. So the distance between these molecules or atoms, it is fixed. So what will happen if you push them close to each other? Okay, they want to maintain this distance now. So what will happen if you push them close to each other? Yes, anybody? Anybody? Pressure. Okay. So question is, now under equilibrium, the distance between these atoms or molecules, it is fixed. Okay, why it is fixed? Because they settle at such a distance where the attractive and repulsive forces are balanced. So what will happen if you push them close to each other? They want to maintain their equilibrium state, and that's why they will push each other. Okay, they will repel each other. Okay, and what will happen if you increase the distance between them? Then they will attract each other. Okay, so same thing I'm sorry, same thing happens for this rope. Okay, so what happens is, let's suppose we have this rope and we connect a mass over here. So there is gravitational force which pulls that mass downwards, and due to which this rope, the string or wire, it gets stretched. So what happens? The distance between these molecules increases a little bit, and that's why now molecules want to restore their initial distance, their equilibrium distance, so they attract. Okay, so when distance increases, then the attractive force dominates the repulsive force. Why what will happen? There will be a force, attractive force now between these molecules. Okay, okay. Yes. So is the thing clear? Okay, video got stuck. All right. So what I was saying is, there is this. Okay, this is a rope. Okay, this is a rope, and it's connected to this mass. And suppose it is hung. Okay, so there will be some gravitational force acting on this mass, due to which there is little extension in this rope or spring or wire, and due to which what happens, the distance between these molecules increases. It's clear now? Is it clear? Okay, can you see the video now? Okay, still lagging. So now it's okay now? Okay, good. So here we have this string, okay, and we connect this mass. So now what happens is, uh, if we hang this mass somewhere, then there is gravitational force acting on this mass, due to which this string or rope or wire, it gets elongated a little bit, and due to which the distance between molecules also increases. Okay, but molecules want the equilibrium distance. Okay, if distance is more, there will be an attractive force dominating the restoring force. There will be attractive force acting between the molecules. If distance becomes less than the equilibrium distance, then there will be a repulsive force. So in this case, what happens when the string is under tension, when some external object, some external agency is pulling it, then the distance increases, and that's why they want to restore the tension, sorry, they want to restore the distance, and they start attracting. Okay, so there is an attractive force acting between the molecules of that rope or the string, and that force is known as the tension. So is it clear? Is the concept of tension clear? Yes? For everybody, is it clear? We can model these molecules as balls like this, and the molecular forces as springs. Okay, why? Because when they are pushed close to each other, there is repulsive force, and when they are pulled apart, there is attractive force. Okay, so these bonds, they behave like springs, we can say. Okay, so now when some external force is applied, so when we pull a string or a rope, what happens? These springs, these bonds, they get stretched. Okay, and they want to restore them back. So there is a force, a restoring force acting between these molecules, and it is known as tension in the string. No, distance between them is not constant. We we exert an external force, so distance between them changes, and that's why there is restoring force. Okay. Yes, Tejasvi, is it clear? Please comment if it is clear. Okay, good. For others, is it clear? Yeah, welcome. So, is it clear for others? Okay. So, what I am saying is, these molecules are at such a distance from each other where the attractive and repulsive forces between the charges are balanced. Okay, so if you push the molecules close, what will happen? The distance will decrease, so they will start repelling each other. Okay, so this distance where the forces are balanced is known as equilibrium distance. So in normal condition, when there is no external force acting, the distance between molecules is fixed. But now when you push them close, they will start repelling. That's the restoring force. When you pull them apart, they will start attracting each other. So what happens when we put a load like this? Okay, this is a rope and we connect a weight like this. The distance between molecules gets increased. Okay, it increases. So now they start attracting each other. Okay, and that force of attraction, or the restoring force, it is known as tension in the string. So is this clear now? Okay, somewhat. All right. So now let's talk about direction of the tension. Okay. So if we consider this string, so these are molecules. Now here we apply a load. Okay. So at this point, the force acting on this rope is downwards. So what will be the direction of tension in the string? It will be upwards. Okay. So the direction of tension is always opposite to that of direction of pull. Okay. So if we are pulling it in this direction, the tension will be upwards. But now the string is, let's suppose it is connected to some rigid support like this. It's connected over here. At this point, in what direction the force will be directed? Okay, thanks Sarvesh. So let's suppose we break this string at this point. So from this sorry, so here the weight will be acting downwards, so tension will be acting upwards. Okay, but now what will happen over here? Okay, bye Gangadharan. So what will be direction of tension? This rigid support is actually this rope. Okay, it is pulling the rigid support downwards. So rigid support, according to Newton's third law, it is pulling the rope upwards. Okay, so what will be the direction of tension now? So here the external force is due to this rigid support. It is pulling the rope in upwards direction. So tension at that point will be acting downwards. Okay, is it clear? Let's see another example. So suppose we take a pulley and let's suppose there is this rope passing over a pulley, and there are two masses. This is mass m1, this is another mass m2. So this is the same rope, So it gets stretched, let's say, by equal amount everywhere. So tension in this rope is equal everywhere. But what's direction of the tension? So at this point over here, the gravitational force is acting downwards. Okay, it is m1 times g, but the rope will be pulling this mass in upwards direction. Okay, so pull on the rope is in downwards direction, and as we have seen, the tension is opposite to the pull. So tension will be directed like this. So at this point where mass m2 is connected, the gravitational force is downwards, tension is upwards. Now what about, okay, so we have seen here the tension at this point and tension at this point, they are directed in different directions. Okay, so what about this point? So at this point, if we consider this left side, then the tension will be acting. So if we consider this pulley, okay, so pulley pulls on the rope in this direction, so tension will be acting like this. Okay, but in this direction, sorry, so this is the pull and this is tension. And what about this side? On this side, tension will be acting like this. Okay, so is it clear? So tension has no specific direction. It acts along the rope, but if the rope is like this, then tension at this point will be directed like this. At this point, it will be directed like this. Okay, so it always acts along the rope. Sorry, what I'm saying, tension always acts in direction of the rope, okay, or string, or let's say a wire. So at each and every point, the direction of tension will be different. But how to find out the direction of tension? So tension always acts in opposite direction of the pull. Okay, so what if you consider a section of a rope, then this part of the rope, okay, so let's suppose this rope is under the gravitational force. That means there is some mass connected. So this part will pull the other part of the rope in downwards direction. Okay, and this part will okay, it is holding that weight, so it will pull this this part in upwards direction. Okay, so what will be direction of tension now? The direction of tension will be like this. Okay, let's call them part A and part B. So part B pulls part A downwards, and tension is always directed opposite to that of a pull. So tension in part A is directed upwards. But what about part B? So part A is holding the part of rope which is below that, okay, and also the weight, so it is holding it upwards. So part A is pulling this part upwards, so tension in this part will be acting downwards. Okay, so if we consider, if we break the string at any point, okay, if we consider a section of the string, then tension is directed opposite. Okay, if we consider two parts, then then tension in those two parts will be directed opposite to each other. So is this thing clear? I'm sorry. Yes, please reply. Tension in part A, B are in opposite direction. Then tension will not be there, so they will cancel out each other. How come they will cancel out? They are not. See, tension in A is acting in part A. Tension in part B, it is acting in part B. So they are not acting uh, on the same part. Okay. So tension in part A is force between molecules of part A. Tension in part B is force between molecules of part B. So they are acting on different molecules. All right. So it's a, I can say it's a big tension to calculate tension, direction of tension. Okay. But remember, tension is always directed opposite to that of pull. So it will simplify finding out direction of tension. Okay, tension is always directed opposite to that of pull, right? So that's tension. And then comes the normal reaction. Okay, so we have been talking about the normal reaction since first lecture on this chapter. So what is normal reaction? So now let's consider this bag. Okay, so if you hold a bag in your hands, what happens? The gravitational force acts in downwards direction. So to counter that, you exert a force in upwards direction, and that force is known as the normal reaction. Okay, so now if you keep that bag on, let's say this table, so gravitational force on the bag acts in downwards direction, so this bag pushes on the table in downwards direction. So to counter that gravitational force, this table has to hold, okay, that bag. So it has to apply an equal and opposite force so that the bag remains in equilibrium. So that force is known as the normal reaction. Okay, so normal reaction is always normal to the surface. So normal reaction is always normal to the surfaces in contact. Okay. And what could be the origin of normal reaction? So if we consider our molecular model like this, then at this point what happens, due to the weight of this bag, the distance between molecules, it decreases. Okay, so we talked about the molecular force. So this is, let's suppose, surface of the table. So there will be molecules and there is a molecular force. Now when you put a bag, what happens? That bag pushes down on the table, and that's why what happens is the distance between molecules of tables, it decreases. Okay, there is a little sag. It's not visible, but there will be a little sag in the table. Okay, so now what will these molecules do? They will try to restore that distance. Okay, and that's why there will be an upwards force exerted by the molecules, okay, by the surface now, collectively this surface on the bag, and that force we call it as the normal reaction. So is the normal reaction clear? Okay, good. The next force is friction. So it's already 8:30. Let's stop at this point. So next time we'll talk about the friction. Okay. All right then. Good night. Okay. Bye.